Hi everyone, this is Joanne Sanoga. I am continuing on the video that I shared with you a few days ago that did not have the visual drawing part that I was trying to make. In that video also I made a few mathematical errors where I used a 14.7% instead of a 1.47. But that's not too bad because we can learn something. I kind of wanted to further iterate about negative predictive values and why this is important and how to integrate that. So without further ado, I'm going to start by drawing here at the 2x2 table. So I'm going to draw two tables because since I shared with you the other numbers, the 14.7 positivity rate, I want to share that as well. But here 1.47% in our population of 2030. That applies to both, okay? And since you did not see what I was doing, one important thing I was kind of going back and forth was true positive, true negative, false positive, false negative. But it's so easy, but so critical to construct this. So the true positive always goes here. But they have like this diagonal relationship that you always have to keep in mind. See how I did it so many times, right? So true, negative. But the easy thing about this, once you do that diagonally, just know that everything makes sense. So true positive, false positive would be here. See how the positive on top and negative on bottom. So in the other numbers for the colon cancer screening, it was 67% sensitivity rate. So the sensitivity rate is over here, that number, whatever variable that is, right? And the specificity was 91%. So whenever you are, I guess this is the formula. So true positive divide by false negative plus true positive. Whereas specificity is true negative plus, divide by true negative plus false positive. And you get the 91%. So whatever number that is. So we have a positivity rate of 1.47. So I'm going to multiply my 0.0147 with the 2030. And the number I get here is 30. So 30, I already have that, is this 67%. So I say 67% times 30, or 0.67 times 30, I get 20. And when you see 30, 20, now it's going to be all plug and chug moving forward. You get 10. Again, those conditional probabilities are very right on, but remember we already have the population already, so this is a cheat sheet. So 30 minus 2030, we get 2,000. Great, so 2,000 times 0.91 is going to give me my true negative. And that number turns out to be, let me look it up here real quick. Turns out to be 1820. So when I look 1820 minus 2,000, then that is 180. So when you look at these numbers, they all add to 2030. Isn't that amazing? I just constructed a 2x2 table out of the base theory, like the conditional probability. So why is this important? Because I can get my negative predictive value when I do that, and I can get my positive predictive value when I do that. So that was the true number that I wanted to relay with a 1.47 probability. So when I calculated the other one, it turned out that it was 200 over here, 100 over here, and 1574 and 156, something like that. Anyways, so again, negative predictive value is what I'm gonna get out of here because I kind of want to talk about that. So, and a positive predictive value. And I'm gonna give two examples about this. So with the negative predictive value for these two numbers, I got here a 94%, whereas I got a 99.5% here. Why is this important? Oh, sorry, it's the other way. Yes, it is this way. See how when there is a low prevalence, the negative predictive value is very high. So when there is a high prevalence, high positivity rate, the negative predictive value is slightly lower. So what does that mean? So when COVID testing came out, people talked about negative predictive value and crappy sensitivity. They kind of compared it with sensitivity, which was cringing to me. I'm like, no, this is not the way it works, right? Because they were sort of kind of trying to talk about maybe the false negative rate, possibly. But the negative predictive value comes when there is a population and you are comparing it over time, or you're comparing it with another. So it's either spatial or you're comparing it with another area, just like what I'm doing right now. It has to be comparable to talk about a negative predictive value. But okay, so now that I've told you, so earlier on we were doing a second test because of our false negative rates were a little bit high. So generally you want your false negative to be low, but they were high. So which meant that the patient was having COVID symptoms, but their test came back negative. So we had to do a second test. But if you were not even doing a second test, maybe now you're thinking about serology because you're like, well, we have to follow protocol in order to, get reimbursed for what we're doing, especially in the ICU. ICU is very critical, right? To have a trail of saying this patient had COVID, but the test came back negative. It has a big implication when it comes to treatment, as you can tell. But then some, states or counties had low positivity rate. So what did that mean? Their false negative was the probability that the person had a negative screening test, didn't have COVID was true, right? Was high, 99.5%, meaning they did not need to take a second test once this person who was screening had a negative test, it meant truly negative. So it is important too, like in different phases, to know when to do a second test and kind of conserve your resources. So that is the main takeaway that I really, really wanted you to know. I know it's a lot of work here, and that's how excited I was last time, but you couldn't see this. So I kind of look like I'm just kind of talking to space, but that's okay. Here it is. It all makes sense. So I'm going to clear this part, and I am going to give you another concept real quick. So again, isn't this our best friend now, right? So I'm going to talk about something called type 1 error and type 2 error. See, type 1 error on top, type 2 error on the bottom. False negative, right? Positive on top, type 1. So why is this important? Because And one thing I miss about positive predictive values, my apologies, it's late in the night and I'm recording this, but positive predictive value, I want you to think about malaria again. I mentioned it in my video last time, but malaria is it's prevalent in Africa or in South America, right? Or Asia, but there is low prevalence here in the US. So if a person was testing for malaria here in the US, there is a high probability that that test is going to come out false positive. So what does that mean, right? Because it's a very, very low number. Remember when I said that you kind of want to have that number very low, because then it's the probability is going to be very low. Okay, that did not make sense. But it's like 1 in 10,000, right? 1 in 100,000. So that is a very, very, very low number when we talk about PPV. PPV is, again, this divided by this. So what is your probability? Very high that the false positive is going to happen. So that's kind of type 1 error, right? So I'm glad I even talked about it here, because we're going to say a hypothesis. So I give you an example of malaria to hone in my point, but I'm going to go back to colon cancer, because that's where we were doing. So when I put this little 0 here, it means now. And this is my hypothesis, alternative, right? So let's use COVID because it's so relevant right now, right? Okay, so let's start. So the fact, okay. So patient has COVID. Patient doesn't have COVID. Or patient is non-detected, doesn't have, let me just fix that. So type 1 error would be the patient doesn't have COVID, but the test detects it. Wow. The patient doesn't have COVID, but the test detects it. Detects the test. What would be like you're thinking? I think this even happened once, where they showed in Kenya or Malawi, one of the African countries, where the bananas were testing positive for COVID, right? And you can imagine the COVID, anti-COVID, anti-mask world saying, the tests are lying, they're over-exaggerating the numbers. Like, right? So type 1 error, that's type 1 error. And that is so rare with, at least in technology, at least in the US, where we do have the genome for the virus, especially the antigen, right? So maybe the antibody, but the antigen tests are fairly accurate because you have the RNA virus for COVID. So that is type 1 error, right? So I hope that was a good example. So type 2 error would be that, and with type 1 error, there could have been like, other SARS, so maybe SARS-CoV-1. There was this one's hack 2 into whatever, but again, it's a false positive. Type 2 error is false negative. See, type 2 to the bottom. So this is the patient has COVID, but the test detects negative. And I already told you about that already, and the complications of it. In this situation, the patient is in the ICU, is critical, needs proning, needs remdesivir, needs all those fancy things, right? But you can't give that patient all of that because the test came back negative and you have to follow protocol and the patient can die. But as I said, it's you can always, it's a physician's judgment to override certain protocols when it comes to saving a patient's life. So that was my example for type 2 error, and I hope you kind of get this concept of type 1 error, what is type 2 error, and let me know if you have any questions, okay? And I'll be more than happy to go over this with you. Thank you.